We in the energy industry have a new information source, an actual real-time look at what is happening downhole with instrumentation utilizing a wide-angle camera placed in front of a high-intensity light source, a dynamic, real-time, visually intuitive basis for making confident decisions. We started this development thinking that we just had the world's greatest fishing tool, but from the first time we watched a gate valve opening like this, we started to find that we could see more than we had expected. But we began by helping save the rig time, so first I'll show a few fishing examples. For instance, in this case, we've tagged the fish with the drill pipe, circulated around water to displace the mud, and ran video down inside the drill pipe. The operator was now able to see that the tubing fish was deformed and skewed against the high side of the well bore, and this allowed the fish to be immediately retrieved with a fishing tool selected based on the video. Here we see a few perforations and another tubing fish. This is supposedly a chemical cut, but I have my doubts. Here we have some sort of wireline tool fish stuck out of the sand there, and the debris at the depth the casing string is damaged and cracked open. Knowing the size, shape, and orientation of the fish gives immediate insight into a quick solution. Here we have the top of a large downhole cavern, and down in the cavern we find drill pipe which had been inadvertently dropped into it. Cavern's about 80 feet wide and tall. Here we can see even the paint stripes indicating the condition of the drill pipe. And here is a tool joint. Kind of a rare view of drill pipe downhole from the outside and sideways. And some fishing jobs are just harder than others. And they went on down to see what the bottom of the cavern looked like as well, and this is the bottom. However, fishing jobs led us to discover that you can see down at the bottom of many oil wells, so next I'll show a few production logging examples. For instance, this well is only 7% water cut at the surface, and we've gone through thousands and thousands of feet of nothing but blackness. We can't see through oil. But when we get close to the bottom of the tubing, this is the tailpipe, the packer bore, the jewelry, the R nipples, etc., we find the continuous component of the mixture is water, and we can see. When we break out into the 9 5/8 casing there went a casing collar. Most of the volumetric capacity is water, and since we are centralized in the lower portion of the wellbore, we can see what is going on. There was lightweight oil. Here is normal black oil. These holes are actually not perforations. They're the hydraulic setting ports of a hydraulic setting packer. They're not supposed to do that. They're leaking. Fortunately, they're leaking oil, but they are leaking. Of course, that's not our packer. I wouldn't be showing it. Here we have a still picture. Notice what happens when you add full motion video to the image. You can see the flow information. You can tell from the bubble movement that these 3 holes are producing a lot of water. Also, enlarged holes are typical of high flow rate water entry. Here we are already below all the oil and gas production, and we're looking at the portion of the well producing water. Apparently, the top perforation here is the perforation on the high side of the hole has been producing sand and water fast enough to eat out this large gaping hole in the casing. Here we are also below the oil and gas production. Notice that some of the perforations are making the water swirl in a clockwise direction, and 2 inches further down the perforation will be swirling the water in a counterclockwise direction. This is due to the difference in the perforation tunnels made when the gun was laying on the bottom of the hole. And this swirling can really confuse conventional spinner type flow meters. In fact, the normal logs did not pick this up. This is what gas entry into a water environment looks like. It's either a perforation or a casing leak. Next we have a normal production video log. You can tell the difference between the gas entry and the oil entry because the gas bubbles are more highly reflective and they move faster through the water than the oil bubbles because of the density differences. At this point, this well has been shut in and is equalizing. We typically make the first pass in the well with the well shut in or at very low flow rates so that we can see each and every perforation and what it is producing. Then we will open up the well to half or even full flow rates and make another pass to see the higher flow rates. Here's some of the oil in the bottom of that same well. Next is that same well a few minutes later as they've brought it online. And here's that same top perforation producing gas. The hydrocarbon flow is filling up about 1/3 of the volumetric capacity of the borehole here, but we can still see what's going on. Down here is a good view of oil production. This is a fairly prolific well. And we found that almost all wells, the oil and gas is on the high side of the hole. There's enough deviation in almost all wells to keep it out of our way. We do have color cameras now on our units. And here's a perforation in a gas well, spraying in wet gas. There are engineering trade-offs in using color, so we usually use black and white. This customer's well kept loading up with water and dying, so he used downhole video to find the 5 specific perforations that were producing water. And then he used that information to set straddle packers and to squeeze off the water. Here we have a sand control screen, somewhat corroded, but that's a sand control screen with gas bubbling up like an aquarium. This well is inclined about 45 or 50 degrees. You can tell by the path of the bubbles. And a few feet below that, we have the oil and condensate bubbling in. This is lightweight oil, such as is found in some parts of the world, and that is the reason it's not black. And below the oil is mostly water. And here's a perfect screen, sand control screen. This is what it looks like before it's corroded. This is a normal production logging run. Note the depth of each perforation, and we're identifying the fluid being produced at each depth. Here's a perforation producing oil. There's a perforation producing not much of anything. There's a perforation producing both oil and gas. You can see the white bubbles intermixed with the black bubbles from that perforation. Usually we have either oil production or gas production, but that perforation had both. We used to think that because of emulsions and dispersions we wouldn't be able to see downhole, but we found that that's not the case. Here we have they're just opening up the well, and you can see the oil coming in that big hole. This is calcium carbonate scaled up casing. Another perforation here producing oil and water. You can tell by the way it shoots out the oil bubbles there. Rod pumped wells are prime candidates for downhole video. We go down the back side in between the production tubing and the casing. And here's some of the first video of a perforation producing oil as the rod pump is going up and down. So each time the rod pump goes up, the oil squirts into the wellbore. Typically the week before they'll pull the rods and pull the tubing and take off the tubing anchor and recomplete the well without a tubing anchor and set the wellhead back on a dual wellhead or an offset type wellhead and let it produce like that for a week or so to clean up, and maybe shut it in for a day even to clean up further, and then that next morning go in with downhole video down the back side in that annulus below the tubing, below the pump housing, and actually watch each perforation and see what's coming in. At these low flow rates sometimes you can't see the water, it's so clear, but you can see the oil, and that's just as good. Here we have a rare example, in fact my only example, of annular flow, where the oil is flowing up the walls of the tubing. Kind of a thick oil and very vertical at this point in the wellbore, and so that's why this is rare. Although it looks like normal electric line, we actually have a fiber optic element hidden on the inside. That's how we get the crystal clear pictures back up to the surface. It's real time, but everything's being recorded for analysis later. Some of the units are packaged in offshore skids, and of course our best pictures come from wells that have gas or air or nitrogen in them. That's what we have here. This is a natural gas storage well. You can see the large fracture going up and down there. In fact, this fracture a few feet below got so big it was apparent that the drill bit was following the fracture for quite a ways. A few feet below here, you'll see the open face of the fracture. If you look close, you can see the reflection, the crystalline reflections from the face of that fracture. And up at the top, you can see back into the fracture a little ways. Here we have a basalt formation, a volcanic formation with very high fracture densities, fractures going everywhere. Basalt. This is one of our older cameras in which we had the light out front. We've learned it's better to light the whole situation from behind the camera now, so we don't do this anymore. Notice that not all boreholes are round. This is a typical characteristic shape indicating the direction of minimum horizontal stress, and you can tell the fracture direction would propagate upward right there. And you can see why it would be important to be aware of the shape of some boreholes when designing logging tools that have to follow the face of the borehole. Density tools can also be significantly affected by these borehole shapes. Here's a circular borehole, open hole, fracture going up and down. There is a formation up above us that's producing a little water, and that's what's dripping downward. A little pool of water in the bottom of the well here. Very large fracture, kind of a cave. Here we have, after a stimulation or frac job, you see the fracture going across the well bore. The customer was curious to see how much chemicals were left on the face of his well bore. Just found about 1.5 feet of particulates left there, which gave him confidence in that stimulation treatment. It wasn't hurting his well bore. Here we have a fracture going all the way across. This is an air drilled well, the top of the fracture, and there's some water being produced, maybe a little bit of oil. Here we have another fracture producing some fluid. Since it's real time, the operators often stop to see what's going on at a particular place. At this point, they found a gas entry point in which the gas is entering almost tangential to the well bore and at a slight upward angle, and that's keeping the particles in kind of a permanent swirling pattern. Here's just a fracture going all the way across the well bore from top to bottom with nothing being produced. Here we have two bedding boundaries of some sort with a fracture terminating at the bedding boundaries. Here we have some borehole breakout, which gives clues as to fracture propagation directions. Here's a washout or a little cavelet. Did not give them any problem, but they stopped because it was interesting to look at. Here we have a casing on the bottom of your screen there. This customer had a very difficult workover. Come to find out, used downhole video to find out what was going on. And he had accidentally milled outside of the casing, then back into the casing, and back out of the casing again. You can see the boogered up edge of the casing, very shiny there. In fact, the bit down below here made quite a bit of new open hole, and the borehole got completely away from the original well bore. Here we have a whipstock. This is an intentional window. So there's the hard face of the whipstock. You can see the little iron filings on the edge of that whipstock. Up above you can see the casing where they've milled through it. As you get deeper and deeper, and the hard-faced ramp gets you further away from the center of the original well bore, you can see where the mill is cut through the casing and the cement, and you can see the formation. So you can see all the levels: the whipstock, the gap, the casing, the cement, and the formation. And this is what a casing window is supposed to look like. The next customer was performing the same operation when something went wrong. You can see up the top where he started the mill job, but the whipstock has turned 90 degrees right in the middle of the job, causing him a lot of difficulties. If you set the whipstock in an unconsolidated formation, this is what it looks like. Just a black hole. Here we have a bridge plug that's leaking. You can see oil being produced from below the bridge plug. In fact, the only oil being produced from this well was from below the bridge plug. In this section of open hole, you can see some fool's gold or iron pyrite crystals or nodules in some sort of matrix that's been partially eroded away or dissolved away. And although this might look like open hole, this is actually cased hole. This is a producer in a water flood area, a calcium carbonate scale that's filled up a significant portion of the casing. They went on down to see exactly where the oil was coming from. Here we have oil being produced not from these perforations but from below the sand. And here we have a piece of corroded casing. It was interesting because this was the only piece of corroded casing in the whole string. Apparently it was a different metallurgy than the rest of the casing. It was acting as the sacrificial anode for the whole string. Here's another form of preferential corrosion along a seam at the bottom left of the screen. And here we have casing that's been almost completely corroded away. You see the bottom right hand quadrant of the screen where you can actually see out into the cement and formation. The casing's very thin. Some customers are using this in oil fields before they buy them to get an idea of the liabilities they may be buying into or to help negotiate prices. This customer thought they might have collapsed casing. Come to find out they've just got mineral deposits and the solution was obvious. You used coil tubing with some acid and you washed it right out. This customer had the same symptoms but actually had collapsed casing. You can see how the casing's been kind of collapsed up into a ribbon. Sometimes we give good news and sometimes we give bad news. Here we have casing that's been shifted to the side. This was a normal production logging run, but found a rip in the casing here. Sometimes we find things we're just not expecting, such as this piece of trash hung on a collar. Knock that down whole. No extra charge. So as you've seen, we're finding solutions with downhole video. That's the way to look at it. And that concludes this little informal sampling of examples.